Hi all, I'm back. Sorry I've been inactive recently. I've kind of been really busy finally putting a workbench together over in the corner. But today we have one of these inexpensive USB-based digital oscilloscopes coming out of China. 250 megasamples per second, 100 megahertz real-time bandwidth. So they're kind of full of crap. This one's PC Instruments branded, but if you look for the case design, a bunch of different companies brand these. And this really is kind of a turd. ADCs are 8 bits, but there's an enormous amount of noise. You get about 6.5 bits of useful resolution. The bottom bit is just totally continuous noise, even with the inputs terminated with 0 ohms. The software is like flamingly horrible. It plays music when you start it. Yeah. It is terrible. I mean, it works. If you're in a situation where you need a portable oscilloscope, this together with a laptop makes a pretty decent portable scope. Just because, you know, again, it's all USB powered, so you can run it over USB. It actually does come with one of those USB-B to 2 USB-As, one of which is just power, you know, so that supposedly, you know, if you don't have enough, you know, if you have a system that really only wants to allow 500 milliamps from each port, you can spread it across 2 ports and it'll, because it draws a little more than 500 milliamps, so it violates the USB spec. 2 channels. Interestingly enough, if I remember correctly, it doesn't support triggering on the input channels above, I think maybe 50 or 100 megasamples per second, just because, you know, apparently the FPGA design is kind of terrible. I took it apart once before, but I think I'll just pop the lid off again. I think. Where are my Allen keys here? So as you can see, it's got hex keys holding it shut. One size larger. And they appear to be metric. Yep. That looks like that is 2.5 millimeters. Might actually be 3, but whatever. 2.5 works. So I've seen these sold under a number of brands, all of which are basically, you know, like most things coming out of China. You know, there's an ODM somewhere, and a whole bunch of different, you know, little tiny shops will just buy it. And as you can see, there's just a sticker. This was through PC Instruments Mark. I think it was about $300 or $400, but we bought this a long time ago, back when, you know, kind of the whole China boom and China test equipment was new, and it was hard to get a hold of. And on the whole, you know, at this point, I'd much rather just buy like a Regal or, you know, an OON or, you know, one of those bench scopes that hasn't built-in LCD and decent sample memory. Yeah, the sample memory on here is, I think, 1 or 4,000 points. So the sample memory is very shallow. It doesn't have deep sample memory like a lot of stuff. Supposedly it's USB 2.0, but, you know, with the shallow sample memory, you know, it'll update at a few hertz. I think maybe 10 or 20 hertz. But you know, I'm just generally very not impressed with it. It's basically been sitting around unused. So in here we have the device, and it does indeed. So you've got a Cypress device, which, so it is indeed a Cypress USB 2.0 system. And you can see that's actually quite interesting. Look at that crystal. It appears to have, it's sitting on 2 ferrites. And they've got a ground strap to the top of the can. It's an HC49 device. Let me switch to a macro. Alright, so here's this really amusing crystal. You can see it's got a ground strap, 24 megahertz from the look of it. So this is the USB crystal, and then it's got little ferrite beads on each of the legs. So over here we have, so this is the calibration output. So this is just a, presumably, let's see, that is the cal output, isn't it? Alright, sorry. This is ground. Here's the cal output. So this is running off of something presumably over here. That's really interesting. Look at that device there. That is a microchip. I think that is the EEPROM. Yeah, 24 LCO2. So presumably all those pins are grounded, but that's, or they can strap them using that resistor there, and apparently they changed their mind. Over here, presumably this is voltage regulation, Cypress device. Little DC to DC, some caps. There's another DC to DC with some inductors. Option IO for second design, that's really interesting. So parallel. So here's the main device. It is a Xilinx XC2C384 FPGA. Down here we have RAM. So this is presumably the sample memory. Let's see if I can get that to show up. That is an ISSI branded IS6IRL V5128AL. So I would bet this is SRAM. So that's just bust straight into the FPGA. And then over here, here's the hardware trigger input. You've got a relay presumably for scaling. You can see that a lot of this appears to have been hand soldered because there's just flux grunge everywhere. So that's, you know, little adjustment potentiometers, interesting power stuff. And this goes into the can. And the can has two little metal tabs that keep it shut. Oop. Over here you can actually see there is a hole for adjustment potentiometer. Take the top of the can off. Here is our analog signal chain. So this is also positively bodge-tastic. Look at that. That appears to be a that is two I think 0805 or 1206 or 603 caps stacked on top of each other. Lots of unpopulated segments. I would imagine these are op amps. Here's a Max 454. I think that's an analog switch. Here's another two stacked caps. Or it's not stacked, it's just very, very sloppily hand soldered. AD 8009. And then this is presumably an op amp. I don't recognize that chip logo. And then here we have input attenuation resistor, or relays, 1 amp, 30 volt DC. These are little half amp 105, 5 volt switching relays. And you can definitely hear these click when you change the scaling. Oh, sorry, that's not a potentiometer, that's a screw. So that allows them to mount it in. And you can see the two channels are, oops, so here's one channel, and here's the other. I think S67441 or SS7441. See if this one's any more readable. It's got an I on it, but I don't know who made that. Just, you know, generally horrible soldering. I mean, it looks like a lot of the stuff was patched after the fact. I mean, this is fairly obviously, it looks like they're switching some of the gains for this op amp, I would imagine. The two channels are, the layout in the channels is exactly the same. So then the two outputs run through here, and then here are the ADCs, which are not in the cans, and they are, and it looks like they're analog devices stamped 9283 BRS. So they may actually be not knockoffs, but it wouldn't surprise me if they were. Here's a Max 434, another one. So they may be switching the references. D2. That's a diode. Oh, that's interesting. Here's some more interesting stuff. Here are some resistors with traces across the pads. So these may be cuttable jumpers. That seems very strange. And here's a potentiometer. This is interesting. 250 megahertz per second, 100 megahertz bandwidth, 512K by 8-bit per channel. So that indicates it should be 512 kilosamples per channel because it's the ADCs are 8 bits. I don't know why the performance is so terrible. There's just some discrete logic. So you can see down here there's a 1.06. Same op amp, it's just covered in flux. I mean, a lot of the stuff appears to have been hand soldered. There's some transistors here, discrete transistors. This is the triggering section. Here's another Max 454. Lots more devices, little 0-ohm jumpers. That's interesting. So this is all clearly trigger related because you can see it has apparently a test point for trigger right here. This interests me. Option IO for second design. I wonder if this has like an 8-bit logic analyzer attachment or something along those lines. And then finally the USB interface is a size 7C68013A. So this is just one of their 8051 micros with USB 2.0 connectivity from Cypress. It's got a red-green LED here. Linear tech switching regulator. This is the external ground clip for calibration. Here's another little switching regulator. Oh, that's interesting. Look at that. This is marked L403, and there's a single box. So I wonder if these are... I think this was like a common mode choke, and they replaced it with two differential, or two just simple chokes. That's really interesting. And then look at this. The output, this pin of this choke isn't even going anywhere. That's RC450. Can't tell. The silk screen's coming off because it's a piece of junk. But more horrible soldering. I mean, it looks like that's a via. I wonder if there was a bad via on this board. Here's another little voltage regulator from the look of it with some little ferrite beads and capacitors. And that is running over here. I wonder if that's one of the core voltages for the FPGA. The one thing I've noticed is there's no configuration memory anywhere on this board, so I think the configuration for the FPGA is dumped over the USB connection when you plug it in, which is a very common technique. Here are more of these interesting ferrite bead footprints with traces running underneath them. I guess they're just too cheap to bother. More horrible soldering. It's really impressive how bad the soldering job on this is. Let me switch lenses again. So here's just a general overview. You can kind of see the overall topology. Here's the little label I was noticing earlier. Just all the RAM buses and presumably termination or some sort of resistors. Horrible soldering. Here's the cal output. Let me take the board out of here and see if there's anything on the back side. Because some of the stuff, like the calibration output, there's no traces running to it, so I think that's got to be on the other side of the board. Oh wow, it's quite busy on the other side. One thing of note is that both halves of the case are covered in aluminum tape. So down here we have all sorts of fun jazz. So this is presumably all sorts of fun input compensation. So these are right underneath the attenuation relays on the input stages. So presumably this is high frequency compensation for whatever sort of attenuation they have. So over here we can see more horrible soldering on the bottom of these potentiometers. Just who makes those? Huh. Oh, that's really amusing. So these are Born's potentiometer knockoffs. They use the same numbers. In this case it's BAOTER 3296. So it's the 3296 series. It's a knockoff of the Born 3296 with a different brand name. China is just utterly. Sorry, camera overheated and I use it as an excuse to switch lenses. So here's the knockoff potentiometer. It's done in exactly the same style as Born's, but it's made by BAOTER MCHC Electron. They're just utterly unabashed about the fact that they're just going to just totally knock off I mean, they just don't have any compunction. It's kind of terrifying. Exact same. I wonder, it looks like the moldings are the same too. I bet they're just a direct clone. They didn't even bother doing any redesign. So down on the bottom we have two canned oscillators, which are clock sources for the FPGA. This one here is 100 megahertz. This one here is 125 megahertz. So presumably they multiply this by 2 to get 250 megahertz. What I've noticed, just look at how amazingly bad the soldering job on that is. It's not even on straight. I mean, I guess it worked, but I mean, just, and here's more. Here's some of the solder points for the cans. I mean, just look. Is that, yeah, that's two resistors stacked on top of each other right there. I mean, that's just wow. And you can see that all of the flux from soldering the relays down is, they never bothered to clean it. And here's the BNC connector flux. It's just, and these are compensation capacitors. That's interesting. So this is one input channel, this is the other one, and they've got different compensation caps. So I mean, some of the stuff, I mean, it looks like some of these devices were hand soldered from all the flux. Q7, Q6 little transistors. I mean, I wonder if they changed some devices out after the fact or something. Here's an 8034. That's analog device branded. Whether it's authentic or not, we don't know. Here's the compensation on the trigger input. So over here, so this is the calibration output, and this is obviously the calibration signal trace, which runs to, it appears that that's maybe potentially coming off of the Cypress device, because this is the Cypress, this is the underside of the Cypress device. The FPGA underside is right here. That's what all of this stuff is. And presumably this is maybe the 1.2 volt core voltage the FPGA wants, or something along those lines. Though it appears to be running some of these devices. Let's see, so if we flip over, so that is this trace right here, which seems to be running to, so maybe this is like that's a 3.3 volt rail, I would imagine. Interesting trace layout. I mean, look at, they've got the traces necking down. There's a little tiny floating bit of copper that's got a V in it for no good reason. More of them. They've got, I mean, it looks like they poured planes, and they, rather than removing some of the islands, they just said, fuck it, we'll stick a V in it and ground it. I don't really think that these planes are going to have any significant, you know, effect on EMI. And that's interesting. Look at, there's a trace cut. There's a cutout in this ground section here. I wonder what that's for. Presumably some sort of EMI control. Got big power traces rolling everywhere. Chinese part number. At least it has labels. Kind of nasty galvanized or tin steel, and it's rusting through. So anyways, that seems to be about it. Place for an unpopulated device. Here's the USB interface. So I wonder what the devil this was. This must be an ESD protection device, because it's only connected to ground and the two USB data signals. So that's kind of intriguing. And then you can also see they've got a 0 ohm, so they're capacitively grounding. So here are the two shield grounds. Well, one of them runs over here, and then, so this is grounding the USB ground. And then they've got this is, and then here's the USB 5 volts going through a ferrite, and there's a reverse bias diode, or a negative voltage. That's weird. So here's the USB 5 volts, and that runs over to this via, goes through this ferrite, and then let's see. Okay, yeah. So then also from here, it pops up to here. This is also USB 5 volts. So then this goes through this big chunky ferrite. There's, look at that, there's via stitching here. This may be a 4-layer board. In fact, I'm almost certain it is. because there's no reason to have those vias there if this wasn't a 4-layer board. It makes a lot of sense that it's 4 layers, but I'm surprised they bothered. It doesn't look like it's 4 layers. So then this is presumably, I would bet that that's 3.3 volts, and then this over here might be, let's see, the trace for that runs over there. I'm sure they've got a lot of power domains. It's kind of interesting. Here's all the flux residue from them glopping this giant blob of solder on the EEPROM. Is that I'm using USB port. There's the ground clip lead with lots more solder all over it, and they didn't. Oh, at least it goes through the board. It's a through-hole part. Because if that was just service mount, that would tear the hell right out. Channel 1, channel 2. Look at that. There's solder balls left floating around. So there's Cal. It's labeled Calogis. That's nice. Actually, what is this? That's just R95. VR831. Not their little devices. So anyways, so there's the inside of an amusingly horrible USB digital oscilloscope straight out of China, complete with the expected quality. And I hope you found this as amusing as I did. I hadn't really looked that closely at the circuitry for this before, and it's about as much of a train wreck as I thought it was. But it's more of a train wreck than I remember. Other interesting stuff, you can see there's a little bit of heat shrink here to try and prevent it from shorting out to the aluminum tape that they're using as EMI shielding. And there was a spring on the bottom that basically grounds it. So there you go, hope you enjoyed.